My name is Frederic Van Haren. Until the beginning of the month, I was the Senior Director of High Performance Computing at Nuance Communications. I decided that I wanted a little bit more adventure, so I became a technical consultant, and I spent more than 50% of my time still on Nuance. Going straight into it, so high performance computing. So why does Nuance need high performance computing? So mostly Nuance is known for speech recognition. So speech recognition is a statistical application where you're comparing something what you are saying against what we call a language model. A language model is a statistical representation of all the data we own. Just to give you a sample on how a typical recognition happens is when the recognizer is asking for a yes-no answer from you and you're a native speaker, then typically the recognition, once you say yes and you're a native speaker, it will say, for 85%, I think you said yes. For 10%, I think you said no. And for 5%, we actually had no idea what you just said. The problem with this whole thing is that 85%, in some cases, if you're using Siri or some other consumer version, it's okay. If you're in the financial business, legal business, or healthcare, 85% is really, really bad. At least if you're on the other end. So how do we fix that problem? Well, the first thing we do is to collect more and more data from the users that are using the system. So for example, one of the banks we used to work with had a very low ratio, below 85%. And the reason for that was very simple. They had a lot of non-native speakers. So in order to bring the non-native speakers on par with the native speakers, we started collecting their usage data and would process that through a high-performance computing environment. Now, so that's the whole high-performance computing concept. So Nuance has an I/O problem. The faster we can process the data, the better. We always are more willing to collect the data, but we're not always have the ability to process more data due to hardware limitations. So it's a 64-bit, Linux 64-bit, no Windows in any way or form. If you look at the high-level architecture with storage on top, we divide our storage in two types of storage. One we call static, which fits the worm profile, meaning it's incoming data. We don't modify that data. We store it. We read it a lot of times. And then we have scratch data, and scratch data is the heavy-duty read-write. So for scratch, we would use SAS drives. For static, we would use SATA drives. In order to make that all work nicely together and export file systems to the users in a nice way, we use technology from IBM called Gpfs, which I believe the new name is Spectrum Scale. And that's the technology that pretty much logically glue all the storage devices. Why is that important? Well, we can replace any kind of storage device attached to Gpfs with newer equipment without the users knowing, but bump up performance and reduce latency. I talked about speech recognition. The other thing that the high-performance computing environment is used for is natural language understanding. So speech recognition, the only thing it does is it converts voice into text. Once you have the text, you have to put a meaning to it. That's what natural language understanding will do for you. Predictive keyboard, if you use a cell phone or an iPad and you swipe over your keyboard, that's predictive keyboards. It's also based on statistics, meaning you swipe over a bunch of letters, and statistically, it's going to pop up the highest, the word with the highest percentage. And also a little bit of text-to-speech. Although text-to-speech is not that high performance, or doesn't need that much high performance, it's part of the environment. VDI. So why is VDI important to us, considering we have a high-performance computing environment? Well, the high-performance computing environment, we only want to run production on it. We don't want people to experiment left and right. So we created a virtual environment next to it that sees the same file, same data, but on a virtual machine where they can do as much damage as they want as long as it doesn't hit production. VDI is all based on KVM. So we build our own EC2, if you wish, equivalent, so our users can create, delete, rename, suspend, all that good stuff. A typical virtual machine is 2 cores and 8 gigabytes. And we deploy hundreds of them. The reason why VDI is also important from a technology perspective is that this is the first area where we started using Flash to help our VDI. So there will be a little bit more about VDI later on. More interesting pieces is the sizing of the environment. So all the numbers on the left are usable space. So we do have a majority of blocks. So the scratch and the static I talked to you about, it's all block. We started introducing OpenStack Swift based on object. So we just buy JBoss, SATA drives, apply OpenStack Swift on it, and expose this to our users. That's for about 2 petabytes. From a server perspective, the interesting piece there is we have 20,000 CPU cores today, but we're moving away from CPUs. We're moving to neural networking, which is based on, let's call them the accelerator cards. It could be a Xeon Phi, it could be an NVIDIA, it could be a GPA, it could be anything, as long as it's more performing. Why is that? Well, first of all, the Intel CPU, the technology we use to do speech recognition today is hidden Markov. It's tied to 1 core. So in other words, 1 recognizer, 1 core. If your product does 1 million recognitions at the same time, you need 1 million Intel CPU cores. Not cheap, takes a lot of space. Moving to neural networks allows you to go much wider. So now you're looking for technology where you have a lot of cores. An accelerator card will do that for you. We have about 700,000 GPU cores now and moving up the food chain. CPU core is a lot faster than a GPU core. That is not a debate. The reality for speech recognition is it's not the speed of the core that is important for speech recognition. It's the amount of cores you can throw at it. It's how wide you can go. Metrics, 1.9 petabyte. I think today we crossed the 2 petabytes of data processing on a daily basis. We collect from our users or from the market over 1 billion new files. And on a good day, the read-write profile is 85/15. I say a good day because it's a research environment, so anybody can do whatever they want within limits, and the numbers can change. So growth rate. So I talked about the 85% success rate. Why is it not 90? Why is it not 92? Well, 85% is the point where if you want to increase to 86 and 87% just by collecting data, you would have to double your investment. So you have to find different mechanisms to increase the 85%. We don't delete data. As you recall from the beginning, speech recognition is all about a statistical application. If you change your statistical model, all the assumptions you made about the data you included and excluded in your language model, it's all back on the table. So there's a continuous process of reprocessing the data. Evolutionary versus revolutionary. So that's where you will see the difference between me and my colleagues in the company is what I mean by evolution is you replace a 1 terabyte drive by a 2 terabyte drive, 4 terabytes, 6 terabyte, whenever that technology comes out. However, that is, considering the growth rate, it's not a good strategy, and actually a strategy that will fail over time. So I would like to use the revolutionary approach. So what I did at Nuance is reached out to storage vendors as Kaminario and trying to understand what they're doing differently than the others and how their technology could work for us, and if it's evolutionary technology or revolutionary technology. Everybody wants it. Everybody wants good performance, better performance. What is more important to us is that it's predictable and consistent, right? So if you buy 1 storage device, you get a certain amount of performance. If you add more of those storage devices, you want that performance and the latency you're getting out of it to be predictable and consistent. Cost per gigabyte. probably obvious. Reliability is another one that is key. Our high-performance computing environment is one big environment, so if one storage device goes down, that is a big issue for us. So high availability to limit the downtime.
Hey, Frederic?
It's really important.
What sort of, a lot of these solutions these days have compression, compaction, reduction kinds of things. Do you see that very effective in your environment?
Yes, actually, I have slides where I will separate those. We reached out to Kaminario. We did a POC with 4K blocks, with 2 shelves each. And the main features we're looking for were performance, latency, scalability, and dedupe compression. And then, yeah, go ahead.
How many other POCs did you do?
In the last year, month?
Did you do Kaminario with a number of others?
Oh yeah, we do POCs all the time. I have two people on my team that do nothing else than POCs. So what we like to do is not just test a single device against a single use case. We try to apply the use cases we have internally where we believe if we have enough test results based on those use cases, that we can make decisions on which technology is going to work out for us. So the first use case was the metadata. Metadata basically means with Gpfs you can separate your metadata from your actual data, which is key for performance. If you look closely, the metadata looks like a database, like a flat file database. Tiering is probably not the right word here. The idea here is we have 15,000 spindles. How do you go to a flash solution or an all flash solution? You're not going to swap all your drives out overnight. You have to find a mechanism where you can start adding flash, make flash work for you, and add more flash as you go along. VDI was an interesting one because we have about 800 virtual machines pretty much running the same Linux version. The last thing we want is to have 800 copies of that operating system. So we wanted to understand from a dedupe and a compression perspective how that can help you. And then high availability and failover. It's overlooked a lot, but we really try to break devices to see if they can recover, or at least keep performing while they have issues.
So just a quick question. The block stuff is all still using Gpfs?
Correct.
So why did you feel you needed high availability at the storage layer when those sort of features could be built into Gpfs? Or were you not using those in Gpfs?
No, we're not using that. So there's another slide I typically present which goes deeper. So what we do is we buy storage devices in a rack and we create file systems across multiple storage devices.
Okay.
And so that's how we create RAID blocks. And in theory, we can lose complete racks, but we do want to understand from a device perspective is how easy is it to cripple it? I mean, if you pull out one power supply and it doesn't fail over correctly and it doesn't fail over, then obviously that's a device we prefer not to put in our rotation, because once you do that, it's like a domino effect. And believe me, there are vendors out there where failover and high availability is not high on the list. So now we're going back to Ray's question where do we use dedupe? Where do we use compression? How does that work for us? Scale up, scale out. So high performance computing is not ideal for, certainly not in our world where we have a lot of binary files. The dedupe and compression is really not going to work. Out of test results, dedupe is pretty much 0. Actually, we're just wasting CPU time trying to dedupe. From a compression standpoint, you can get up to 15%, but that's the best you can get out of it. So most of the tests we do for scale out and scale up is ignoring compression in dedupe. 4K blocks, each with 2 shelves. We have a variety of file sizes. A typical sound file is in the kbytes. What we do to store them, we put them in larger blocks. We tar them up in megabytes. And in some cases, if we do it per customer, we do it in blocks of 50 gigabytes. So in order to test the device, we did kilobyte, megabyte, gigabyte, and see what it would do. We tried to break it. Every device has its pain points. We just want to know and understand where they are. findings from scale out and scale up is you have performance for high performance computing. That's where it doesn't matter if there's some latency, but you want pure performance. If you think about VDI, VDI is where actually your latency is a lot more important. You don't want your users to wait 5 seconds for a listing of files to show up. We did notice that with Kaminario, we could push the device a lot harder before latency starts to stretch out longer than with other vendors. In this case, we was sub-millisecond, 0.7 millisecond was actually what we saw most of the time. Other vendors at the same load were giving us a latency that was 10 times longer. IBM Gpfs metadata proof of concept. So we decided to take one of the K blocks purely for metadata data and the other 3 for actual backend data. The workload is the same as scale up, scale out, but in this case, we paid a lot of attention to the dedupe and the compression ratio. Because it's a flat file text and it's structured, we were hoping for huge benefits, and we did see them. Dedupe and compression combined, in average we saw 4:1, and at peak we saw 6:1 ratios. Which not only helps with having to buy less storage, it's also much faster, because RAM is still faster than flash. VDI was actually an interesting use case for us, because when we started doing POCs with vendors, we assumed that we wanted to put the operating system and the user data on the same disks or the same flash devices. What we noticed is when you deploy, let's say, 100 virtual machines, you will see that the dedupe rate is extremely high in the beginning. But once you hand that off to users, users start to modify it. Users start adding data, but the user data is typically not highly dedupable or compressible. So you will see your dedupe rate actually going down. So that's why we put a heavy focus on compression rates. We thought that compression was more important actually than dedupe. What we also learned from this is that if you want a high dedupe rate and it's predictable, you actually try to separate the operating system piece from the user data. If you have the ability to do that, 2 different storage devices. Actually, your user data doesn't even have to be on flash. You can get much better results than combining both. We did see consistently user experience, so from a latency perspective, again, VDI is more about latency than performance.
And you say you don't run that with a broker, right? It's all straight RDP sessions? From a previous slide?
Yes, it's Unix RDP, yes. Yes.
Okay.
So we used a thing called No Machine, a product called No Machine from a company in Italy, and now we are migrating to Spice as part of Red Hat. So transition from hard drive. So we have 15,000 hard drives. I can't flip them all over to flash overnight. What we can do is to come up with an architecture where we start out adding some flash and then see where it would end up. That's what this POC was meant to do, is what happens if we start adding some amount of flash, being it limited, what's the impact? Where are the areas where we can benefit from it? And the first thing we did is after all the other tests, we decided to put the Kaminario device in production, not with primary data, but as a caching device, just to see how flash could help with caching. That worked out really well to the point where we decided to move forward with it as a quote-unquote tiering mechanism, where you start with all your spindles, have some flash in it, and then you keep on adding more flash until you pretty much have replaced your spindles. High availability and failover. For my engineers, they like this one the most. You know, how can you try to cripple the device by pulling power supplies, drives, and all that good stuff? We didn't see anything that disrupted traffic. We saw some blips left and right, which is to be expected, but we did see no major issues whatsoever, which was also a first. Most of the time there is something that fails with a particular device that doesn't allow you to move forward after failure. Reliable and being robust is, for us, high-performance computing, very, very important. In summary, I actually talked to a lot of people from Kaminario before I actually did a hands-on on the machines. What I did notice by speaking to the Kaminario team is that their approach and the design to the Kaminario device is first of all based on flash from the ground up. So it's not like some spindles and then they added some flash and then hopefully the whole thing would work. It was a design straight out from flash. I like technology a lot, so when I started talking about future technology, the response I got was, well, we can look at that and we can build that in the future. The platform can handle it. High performance and low latency, right? So it's typically you can get decent performance and not so good latency, or the other way around. In this case, performance and latency is pretty good. Scale up, scale out. Doesn't matter if you have one or multiple, performance stays predictable. K-rate is helping us with space, so we don't have to buy as many flash drives in order to get the usable capacity. Data reduction, reliability, it's all good. From a use case perspective, it did quite well across the board on all our POCs or use cases we tested it for. The metadata for us was the one with the biggest return on investment, because you go from 4:1 to 6:1, and not only do you have a need for less hardware, you end up with better performing device. Talked a little bit about return on investment, so that is key, right? So you don't want to do the evolutionary thing where you replace spindles with flash. Without getting anything in return. In this case, you end up with less hardware, better performing, and lower latency, and linear performance and cost, which is key. I mean, once you buy a lot of hardware, you want to be able to predict where you're going to end up.